Now that we learn how to draw the three-dimensional structures of various molecules, we can go back and look at the structure of carbon dioxide and see how it acts as a greenhouse gas that traps heat on Earth. I bring back this picture that shows how the energy from the sun gets absorbed and then later on emitted back to space. So all of these are different solar radiation that comes in and heats the Earth. And then we have these collection of gases that includes water vapor, aerosols, which is some of those chlorofluorocarbons or other compounds, all the different varieties of greenhouse gases, all of them absorb some of these energy that's being emitted back. Now, when the sun's energy hits the Earth, it comes in various type of radiations, including UV radiation, as we discussed before, but then when they're being emitted back out, they are all emitted in the form of heat, which is just infrared radiation. These are lower energy, longer wavelength types of radiation. The unique thing about these infrared radiation, which is shown in this picture as these red squiggly lines, is that unlike the UV radiation, which can actually break chemical bonds, these type of radiations has much less energy, so all they do is just make the molecules basically jiggle a little bit. So that's what we call molecular vibrations. The vibrations that the molecules can absorb from the infrared radiation depends on the molecular shape, and that's the reason why we went to VSEPR before, to help understand what type of shapes are possible. Just like we were talking about breaking chemical bonds with UV radiation, we need the UV radiation's wavelength to be exactly the same as the strength of the chemical bond. Here, when you want to have the infrared radiation be absorbed by the molecule, the vibrational energy of the molecule must match that wavelength of the infrared photon, okay? And so there's certain wavelengths that are absorbed and there are other wavelengths that are not absorbed. Now, the reason why CO2 in particular is a greenhouse gas is as follows. So this is the structure of CO2, as you remember from our previous example. It's a linear structure. It has carbon in the middle and then the oxygens on the ends. It looks exactly like this. And there are different types of vibrations that are possible for CO2 molecule. So one type of vibration is what we call stretching vibrations. For CO2, there's two different types. There's types where you can pull on both sides of these oxygen. And then there's another one where you push on both of the oxygens in the same direction. So when you pull at opposite directions on the oxygen, that's called symmetric stretching, whereas when you're pushing on the same direction, then that's called anti-symmetric stretching. Now, it turns out that only one of these vibrations has the same energy that matches the wavelength of an infrared radiation. So this anti-symmetric stretching is one that can actually absorb heat emitted from the infrared radiation. CO2 has two additional vibrational modes of motion. These are called twisting, and then the other one is bending. So I'm showing pictures of these bracelets to illustrate how these bending and twisting motion occurs in a molecule like CO2. If you twist it, then the molecule can behave like this, where the central atom is right here, and then the oxygen are twisted either in the same direction or in the opposite direction. And then bending just looks like this. So here's the central atom goes up, the two oxygen comes down. Both of these vibrational motions are also able to absorb the infrared radiation that is emitted from the Earth. You can tell that those happen because we can do something called infrared spectroscopy. We shine infrared light on a sample of molecules, and we can see these inverted peaks here that tells you that infrared is being absorbed. So you can see here that there's an absorption around this energy value, and then there's another absorption around this energy value. So the one here corresponds to those bending motions that I was talking about, bending and twisting motions. And then this one right here corresponds to that anti-symmetric stretching. All of this is to say that CO2 is quite effective at absorbing infrared radiation. And the reason that matters is because if the infrared radiation is absorbed, it doesn't escape into space. If it doesn't escape into space, then the heat is trapped. It stays on Earth in the atmosphere. And so what happens to this heat that CO2 absorbs? Well, there's sort of two possible fates to those heat. some of that heat is held by the CO2 molecules, and then after a while, it just releases it back in all directions. When it releases it back to all directions, it includes going back on Earth. If you imagine a number of CO2 molecules here in the troposphere, some of the heat is released out there, but some of the heat is released back down onto the surface of the Earth, like this one right here. So in other words, there's some percentage of that heat that stays on Earth. The other fate associated with this energy that's absorbed by the CO2 is that they might be transferred into molecules like nitrogen and oxygen, which, although they're not greenhouse gases, exists on Earth, and therefore that energy doesn't really get released back out into space. So either way, when a CO2 molecule absorbs heat, it keeps much of that heat on Earth as opposed to releasing them into space. And so this is what makes CO2 a greenhouse gas. Now we need to talk a little bit about climate change, but before we can do that, we need to talk about the difference between weather and climate, because that's often become a source of confusion when people talk about climate change in everyday discussion. So weather is just the short-term condition of the atmosphere. So if you go outside today or you look at the weather forecast tomorrow, that's weather. It's telling you what's going to happen the next, say, 24 hours, 48 hours, a week, but it's not long-term. Climate is something that happens long-term. So it's the averaging of all the weather that's been going on for years. Usually we would look at a pattern over 30 years to consider that to be a real observation of the climate. Of course, you can have the climate warming up and still have snowstorms and freezing conditions in certain parts of Earth, because the freezing conditions that occur for, say, 3 months, that's just the weather, whereas the climate is something we observe over 30 years or more. One of the most interesting things observed over a period of 800,000 years is that just around the past, 20 years or so, we see this increase in the levels of CO2 at the same time that we see a change in the temperature of the Earth going higher. Antarctica is the best place to measure this. However, we also see it in the global average. So there is a correlation between the increase in the CO2 concentration along with the increase in the average temperature of the Earth. You might wonder how we measure concentration of CO2 from 800,000 years ago. CO2 is slightly soluble in water, and the reason why we look at Antarctica here is because the CO2 that is dissolved in water is trapped there as ice that's been staying there for hundreds of thousands of years. And so when you take out that sample of ice, you can use current technology to measure the quantity or the concentration of CO2 that exists in the ice, and therefore draw some conclusion on how much CO2 was present when that ice was around some hundreds of thousands of years ago. So we know that CO2 is a greenhouse gas. We know CO2 concentration is increasing. We know the temperature of planet is increasing. So the cause and effect here is pretty clear. Obviously, there's a lot more evidence out there, detailed evidence that you can look into. And I would encourage you to look into that, particularly from the IPCC, which is the Intergovernmental Panel on Climate Change. It's a UN panel of scientists that studies the effects of climate change and the evidence for climate change. This is just one of the latest slides that they posted to show the impact of climate change on different aspects of life, including diseases, food and water access, extreme weather in certain parts of the world, and so on. If you watch the news, you will see some of these happen in different parts of the world, including all these extreme weather events. A lot of the food and water access issues happen, of course, more in developing countries. And so it's really important that we all get more educated about this whole process and see what we can do as individuals and perhaps through our own governments to push for efforts to help reduce the effects of climate change. Just like when we discussed that ozone hole, the situation can be reversed. I hope this is a productive conclusion to this chapter and it helps to galvanize you to want to do some of the work in this field.